Hello? Hello? Cầm nè. Chính cái đời.
Yes, sir. Can hear you loud and clear, Dr. Harun. Sorry, Dr. Harun. I don't see the link in the chat box. Would you be able to share it again in the chat box, please? Thank you, Dr. Harun. Thank you. All right, got it. Thank you. Yes, Dr. Harun.
Yes, I'm here, Doctor. Okay, thank you. Okay. Okay, thank you, Doctor. Good afternoon, all. Can you all hear me? So today I will be presenting on the electric vehicle charging, what's the current and trend and development in Malaysia. First of all, of course, I would like to give a brief introduction of the classification of vehicles. We have ICE engine, or short form for internal combustion engine. Then, of course, we also have the hybrid electric vehicle, which is what we call a mini hybrid. The one that we are more interested in is plug-in hybrid electric vehicle, and also the electric vehicle, or we call EV. Hybrid electric vehicle, it's a combination of ICE and actually electric motor. It has very small battery in a way as around 1 kilowatt hour. It has limited range, and it's actually charged by regenerative braking and also by the ICE engine. Of course, the types of cars which are HEV are like if you were to drive on battery alone, it has a range of 30 kilometers. Cars like Volvo XC90, BMW 330e are some of the plug-in hybrids that you can actually see. And we also have the electric vehicle. It has only the electric motor, has large battery capacity, which can go up to around 120 to 400 kilometers. Cars are like Nissan Leaf, Renault Zoe, and Tesla are some of the models of electric vehicles. Okay, you might be asking, why are the countries in the world all pushing for electric vehicle? In India, one of the reasons why they push for electric vehicle is to curb pollution. Of course, the second and most important thing is they also want to lower the import bill of their crude oil, which can amount to around 70 billion in these 2 years. Then another thing is very interesting. What is grid parity? Grid parity, they have a solar system where the cost of generating from solar PV is almost or equivalent to the cost of generating from a coal power plant or coal power plant. And why in China the development of EV is very big? Of course, you know that in cities like Beijing and Shanghai, their pollution is quite bad. So one of the reasons is the same as India. They try to curb the pollution of CO2. The government actually subsidizes for each car And the government also provide grants for EV and battery manufacturers to actually manufacture EV. China wants to have at least 25% of all cars to be new energy vehicle, which consists of battery electric vehicle, plug-in hybrids, and also hydrogen cars by 2025. Then we have UK and France, which are also phasing out the fossil fuel car by 2040. In Singapore, which is our neighbor, they also have set a target early this year to phase out petrol and diesel fuel vehicles by 2040. This is a very significant milestone for Singapore, where they actually have a plan in place when they actually want to phase out the petrols and the fossil fuel cars. In Indonesia, we also have big auto manufacturers like Toyota. They are investing 2 billion to develop electric vehicle in Indonesia. Hyundai has also announced investment to build their electric vehicle plant there. And we do have Grab, which launches the electric car taxis in Indonesia. Thailand is also the same. They are trying to be the EV hub in 5 years' time. They are giving a lot of pioneer status and tax incentives for the users to actually have that. What are the things that Malaysia is actually going through? Malaysia in EV development, Green Tech has up to year 2030, they plan to have the amount of electric cars, 100,000, amount of electric vehicle charging station, 125,000. That's the goals of our Malaysian government to push for EV development here. For global EV and PHEV sales, you can see from the graph, it is increasing at least 50% year on year from 2012 to 2018. If you were to compare to the overall market share, it's only 2.2% of the world share in 2018. The next slides actually show you which is the manufacturer who manufactured the most electric and plug-in hybrid cars in the world. We can see that Tesla is at the forefront of the industry with their new Model 3, which is almost constitute 80 to 90% of their sales of their overall cars. For Malaysia itself, currently we have about 28,000 of plug-in hybrid and EV cars. You can see from the screen on the left side, Volvo, BMW, Mercedes-Benz has a lot. They are the plug-in hybrid cars where they actually have up to around 27,000. For electric cars, which what we call the pure EV, the number is still small, which is only 200 units. What are the EVs and plug-in hybrids that we can actually anticipate to be launched in 2020 and 2021? One of it is the high-end car that we will be looking at. It's the Porsche Taycan, which will be launching it maybe after the MCO. Then we have the Kona Hyundai, which also is one of a very well-rated EV cars in the world now. Then the interesting that one which we want to highlight is the MG ES, which is this car which can go up to around 300 plus kilometers, and they are actually selling it at a very affordable price, target at 150,000 for it will be the cheapest electric car in our Malaysia market. Let's get technical. What are the things that we actually need to look at it? A lot of times when people talk about charging an electric vehicle car or plug-in hybrid, it is like it actually consumes up to 16 amps, equivalent to running a 5 horsepower aircon. So if you talk to a customer or you talk to a user running an aircon, then you realize that it's actually a very big power kind of charging that we are looking at. What are the different charging modes that are available classification? We have the mode 1 and mode 2, which is the portable charging unit. The difference between mode 1 and mode 2 has a control box with RCDs and protection devices meant to be used for charging an electric vehicle. Then we have mode 3, which is the AC fixed charging stations, which you see in the mall and hotels and in public areas. Mode 4 are those DC fast charger which can charge your car very fast in a very short period of time. What is the difference between an AC and DC charger? An AC charger can take in a 240 watt single phase or a 400 watt three-phase supply. From the EVSE, which stands for the Electric Vehicle Supply Equipment, it supplies the AC to the onboard charger in the vehicle. The onboard charger in the vehicle will convert the AC to DC and it will go to charge to the battery. The limitation of the car charging speed depends very much on the AC-DC charger, or what we call the onboard charger. Then we have the DC charger. The DC charger usually takes in the 400 watt three-phase, goes straight to a web inverter where they convert AC to DC. Then the DC goes straight to the battery. What are the different types of AC plugs actually available? Type 1, or mainly used in Japanese cars like Nissan Leaf and Mitsubishi. And Type 1 is also called SAE J1772. They are also used in North America cars like Tesla and etc. But for Type 2, it is meant for European standards kind of car where it is done and very commonly used in the world. Type 3 are more concentrated in places where in France and Italy where they have additional requirement of having a shuttle at the charging plug itself. For DC plugs, we actually have 4 different types of DC plugs in the world, excluding Tesla, which also has a proprietary system. In Japan, they have a system called the CHAdeMO DC charger. For system B, it's mainly used in China, where it's called the GPT plug. For system C in US, we call it a CCS1 combo, and we have an IEC Type 2 CCS combo 2. These are the look of a AC and DC charger. On the left side, you can see that it's a look of an AC charger where they actually have stand with the charger. For DC, mainly most of the equipment supplier will have some sort of AC coupled with the DC, so it can charge for AC and DC together. In the picture shown here, you can see that the number 2 is actually a CHAdeMO DC charger. Number 3 is actually a CCS combo, so that anyone who uses different cars can utilize the DC charger. Earlier, we have shown you the AC and DC charger. Now, we want to show you what are actually in the car. The picture number 1 is actually a Nissan Leaf, which is actually available in Malaysia. You can see they actually have the Type 1 socket at the car itself. Then for DC, they are using CHAdeMO. For the plug-in hybrid, you see on the right-hand side, because the battery size is 9.2 kilowatt, 11.6 kilowatt hour, they only have a Type 2 charger, which is meant for using an AC only. For the new electric vehicle, like XC40, they will have a CCS combo coupled together with a Type 2 included in the car for you to use either an AC or a DC charger. Where are the places where AC and DC chargers are used? For home and for workplaces like offices, normally they will use the AC charger. It can ranges from 3.7 kilowatt to 22 kilowatt. Normally for homes where we actually park our car for many hours, you do not need a very fast charger. An AC charger will be sufficient to actually charge your car overnight till it becomes full. Then on the second side, where in commercial areas like petrol stations or in Tesco's or hypermarkets, they have a DC charger of 50 to 100 kilowatt. It can actually charge your car within 50 to 60 minutes. Then we have those high power DC charger, which are mainly deployed in highways. you can see from here that the charging speed is tremendously reduced so that people do not need to stay very long in those R&R areas to rest before they go down to the next states or destination. Charging duration. I'm actually giving an example of a Volvo XC90 plug-in hybrid. From here, you can see that they actually have a battery capacity of 11.6 kilowatt hour. The second thing we will be looking at is the charge power. The charge power is the onboard charger, which we mentioned earlier. It determines how much power that can actually be tapped into the car based on the onboard charger rating. From here, you can see that it does not make difference if you were to use a single phase 7.4 kilowatt or a single phase 3.7 kilowatt compared to a three-phase charger. The charging time remains the same at 3 hours 50 minutes. The reason why the charging time does not increase with the different charger is because of the limitation of the onboard charger. Later, Dr. Chi will actually explain more on the architecture of a vehicle so that he can actually go through the onboard charger kind of description to you. The second project that maybe I want to highlight is the project that we did for United Nations Industrial Development Organization. A lot of times when you charge electric vehicle, we actually have zero emission. But some of the naysayers say that even though it is zero emission, but you are taking power from the from the coal power plant or gas power plant, which actually emits and produces CO2 at the other side of the area. So for Yuen, they wanted to showcase that charging can be 100% from renewable energy. This is a standalone DC charger where 100% of their energy is harvested from solar PV system going into a 50 kilowatt of lithium-ion batteries. The 50 kilowatt hour of lithium-ion batteries is used to power up the DC charger at the site location. These are some pictures of the other DC chargers in Malaysia now. We have total public DC charger, which we have now, it's only 4, including the IEEE charger, which is under maintenance now. So currently in use, maybe you can actually use these 3 different types of DC charger. One of it, I think it's located in Kayu Ara. The other one is in ABB office in Subang Jaya. The third one is actually in Nichikon's office in Bangi. Of course, when we first started the EV charging in Malaysia, we will need to have standard to make sure that the products brought into Malaysia has test reports and standards conforming to the IEC. In year 2030, we actually came out with our Malaysia standards for IEC 161851 for the AC charger. At current stage, we are actually with the committee trying to come out with a DC charger standards, which will allow you to either use a CHAdeMO or CCS combo charger. Of course, in Green Building Index and all those green building certification, they do provide points if you were to install EV charger at some of the buildings that are going for green building certification. We have one of it is the Green Building Index. The other one is the Green RE or the Green Mark, where you do score points for providing EV charging stations at your development. Then this is more for concerns for M&E consultants. Designing the single line drawing of the EV charger. Based on the standard of the EV charger, we will need to install a Type A RCCB for each charger protection. It has to be 30 milliamp sensitivity rated and Type A because for the charger. Therefore, the normal RCCB used for household is actually Type AC. That is why for charger, you have a special type A to be installed for protection of the leakage current. And a lot of people has been asking us as well, what are the payments options available for EV charger in Malaysia? The most commonly model, what we call the subscription model. Subscription model is like a extra kind of model where you can actually have paid amount of pay a certain amount per month. You can actually use the charger no matter how many times with this thing. But of course, we know that this model has its pros and cons because we do not measure the time use or the kilowatt hour use. And also, some people actually apply one card and can be used for 2 to 3 cars. Then we have the second option where we actually provide touch and go reader and Visa Pay Wave reader for you to pay per use based on the usage of the charger. Another thing I would like to highlight, in Malaysia, it is you will need to apply for license before you can actually sell electricity from Energy Commission. Even though you apply for license to sell electricity, you will, since the electricity is a regulated market, you will need to make sure that the price that you are selling cannot be higher than what is regulated. So for us, we are trying to make sure that not to go into that route. We actually, based on the touch and go and the Visa Payway system, we will be using time session instead of kilowatt hour to sell the charging session. Of course, the third options, you can actually pay using an app where you can actually key in your credit card and the session, based on how much time session your charging works out, it will actually calculate and deduct from your credit card. The next thing I would like to actually emphasize is a lot of JMB, joint management body and existing condos always ask, how do we plan to actually have an EV infrastructure ready for existing condominiums? Problems faced by existing condominiums. First, of course, a lot of condominiums, existing condominiums, do not have sufficient EV charging stations facility. Even though they have like 2 to 3, but maybe they have a lot of EV and PHEV users where it is impossible to actually have to charge it for every car. Then we also have the issues of hogging of EV charging stations facilities at the place. Because at night, when you park your car for charging, if your car finished charging at 3 or 4 a.m. at night, would you be going down to remove your car and park it back to your original parking location? These are some of the issues that existing condominiums are facing. Then another thing is, even though you let the owners to pull cable or pull power from their DB to their located car park, that, as you know, that lighting DB has a very small power. It can only cater for a few residents or owners which has that. What if 10% or 15% of the owners actually owns the AV and plug-in hybrid? How are you going to manage and tap from the lighting DB? Then we also have issues like non-EV and PHEV residents complaining to the MC. Why are we using common funds to finance EV charging stations at the facility, at the condominiums? And some of the places we also don't have issue. We have issues on the no payment system available. And some of the residents, very innovatively, they use the car washing power point to actually charge their car. What is actually the bottleneck that we are actually facing? From here, you can actually see that normally in current scenario, the main switchboard will go to the sub switchboard and it goes down to the lighting DB at your car park. The bottleneck, it happens at the place where the cables to your lighting DB is limited by the power it is designed for. So the proposed solution is to have a new EV sub switchboard at your car park where you pull a new main switchboard power supply to the new EV sub switchboard, and from there you distribute to the individual DB owners which wants an EV charging facility. But first, of course, if you are an existing condominium or apartments, you need to measure how much excess power capacity that you have at your condominium. From then, once you determine the highest peak of energy or power that was used at your condominium, then you divide by the total number of units which are available in your condominium. Then you will know that how much power can each of the user or the residents be allocated with. Once we get this power capacity measurement from the main switchboard, we can actually modify our main switchboard to cater for an additional breaker to pull for the new sub-switchboard EV that we were mentioning earlier. From here, you can see that each residence will be provided with a DB where they have an individual RCCB for their protection, so they do not disturb the upstream. For this project, each of these residents are provided with at least 7 kilowatt hour of power. They have an isolator and a socket where the use of the isolator if they want to install a charger. As you know, now condominiums and apartments, they are located with 2 to 3 car park bays per units. So this facility can actually cater for simultaneous charging for at least 2 to 3 cars. Then another thing is why a lot of condos which we let residents to pool individual parking, you will have the issues of messy wirings at your car park areas like the picture shown here. So what condominiums or JNB can do is get a contractor, pull a main trunking where the users can actually tap from existing main trunking where they can actually, the wirings can be more neat. It actually caters and makes sure that the visibility and aesthetic look of the condominiums are still intact. From here, of course, you must make sure that each EVDB will need to have an individual protection of an MCB with an energy meter to measure how much energy is consumed by the owners itself. If they don't pay, at least you can actually switch off the breakers which provides power to their designated car park areas. The energy meters can actually be hooked up by an energy management system where the user or the admin can actually monitor the usage of the energy monthly without going down to each dB or each meter to record it manually. Some of the testing and commissioning equipments that are very useful, it's like the Seaboard EV simulator where you can actually plug into the charging stations to get the parameters and the grounding parameters for a charger to make sure that the charger can be used for all types of cars in the market. For some cases, you might even need a standing leakage current detector to make sure that the standing current leakage now in your system is able to cater for more sensitive cars like the Renault Zoe charging at the charger itself. And lastly, of course, in Malaysia, we do have what we call the Malaysia Electrical Vehicle Owners Club. Those who has electric vehicle or plug-in hybrid which wants to know more or contribute, you can actually visit their Facebook page here. Thank you very much. I hope I get to address most of the concerns and the information to the crowd here. Do let me know if you all have any questions. Thank you. Okay, I pick one. Go up to the. Okay, we encourage DC fast charger to be installed at Ipoh and Penang. Definitely, we are also working with some of the players in the highways where we actually intend to put up DC fast charger at this selected location so that owners or people can travel from Penang to KL to Singapore. We are trying to connect the areas between the three major cities. Then for a question from Wong KH, to fulfill for GBI or Green RE requirement, is it mentioned what kind of charging station to be used? Previously, to fulfill for GBI requirement, they only require you to provide isolator, but the latest revision requires you to have at least a physical charging station. It doesn't mention whether it's an AC, DC, or 3.7 or 11 kilowatt. Cost for electricity for EV is cheaper than petrol now. We did a study with the Volvo at current cost of electricity of we mentioned earlier. It is still slightly cheaper to charge from electricity compared to using petrol. But the catch is the return on investment. Buying an electric vehicle car is still more expensive compared to an ICE car. So we are still waiting for a time where the EV the price can be the same as an ICE vehicle. Did I address all questions?
I think there's some question asking about the price difference between the AC charger and DC charger.
For AC charger, it can range from 5 to 10,000 or 15,000 depending on the accessories that you require for the location. For DC charger, we'll be talking about 80,000 to around 150,000 based on different kind of brands and power capacity. So you can actually see a very big difference between an AC and DC charger.
I think there's one more question here. It says, how many days maximum we can leave our car not being used or charged before the battery becomes fully discharged?
I think if you are leaving your car to if you are going abroad 2 to 3 weeks, each manufacturer has a recommended to make sure that your car do not charge has a capacity of 40 to 60% instead of having it full, so you can still maintain the charge and maintain the charge and also the thing in your car. Okay, for condo operators, I think you will still stick back to AC charger. It won't move to DC charger unless there's a business model which recoups back the high cost of investing in DC charger. For us, we always currently in our Malaysia EV standards, we still allow both CHAdeMO and CCS instead of selecting the technology which we think is more superior. Because at current stage, what we can do is we have a charger which we can actually provide 2 different DC charger standards like the CHAdeMO and CCS. For Tesla users, they also do not need to worry about not having to charge in those kind of situations because Tesla has an adapter either for a CHAdeMO to be used or a CCS combo to be used. So we are making sure that at the current stage, both of these standards are still important. We do not know who will be the lead. The CCS seems to be the current leader in terms of the DC charger, but CHAdeMO still has their advantages in making sure that the systems, the the vehicle to grid and all those kind of things which are still applicable. There are no coming cars. What are the questions? Chat box, can we lobby for the government reduction in toll, parking, road tax, insurance? Of course, I think there's a lot of parties now doing their work to actually lobby the government to reduce the road tax and the insurance or the car excise duty for EV. But of course, we are still in the. I think the government is the association and other parties are still in negotiation and working with the government to actually push up the incentives which can be provided to EV users.
Ayarli, good evening. My name is Dinesh.
Yes.
I would like to check with you, is there a TC, technical committee under DSM, Department of Standards Malaysia, working on a national standard or to adapt the IEC as MSIEC?
We do have a committee to do that, and we adopt some of the IEC standards, but we change it to suit the local environment.
Has it been officially released, the standard MSIEC for EV?
Hey, yes, you can. Since 2013, I think the standards already been out for the MSIEC 161851.
Sorry, I didn't catch the number. The number again?
61851.
Thank you.
No problem. I can't get you the question. Say again. Maybe Dr. Chi can answer that question. I'm not so familiar on the power quality on the charger itself.
Yeah, maybe later I can cover a bit. Yeah.
Yeah, can.
Okay, thank you very much, Dr. Harun. Thanks, Arali, for the presentation. So I'm going to continue with what Arali has left. So he has mentioned a bit about the general trend of EV in Malaysia, and he went down a bit on the technical aspect of the EV chargers. So I want to go actually one step further to give some ideas about what is the difference between the AC charger, DC charger. So what is why we are paying so much more. So just now I already mentioned that AC charger goes about 10,000, but DC charger we go up to 80,000, maybe more than that. So this is some information that we gather through our experience working with Arali's company. So of course, I know that I realize that there's a lot of experts in the audience. So I welcome any kind of inputs after or during presentation, after presentation. Feel free to write something in the chat box. We'll try to address all the comments later. Okay, so for my part of the presentation, I'm going to explain about the differences between AC and DC chargers. So I want to explain what is actually in an AC charger and what is the limitation of AC charging. So then what is in a DC charger? And I'm going to briefly explain about the concept of integrated onboard charger, which is what we know as AC fast charging. Okay, so EV chargers. So what's the difference? So if you see these two pictures on the left and right, you can see there's a small little box here. This box here, this is a EV charger. On our right side, this big box here, this is also an EV charger. So the size is significantly different. As you can expect, the price is also significantly different. So the question is, what makes the difference? So of course, this comes down to the two main characters that we are trying to introduce here. One is AC chargers and one is DC chargers. So we always call the charger as charger. But according to IEEE, usually we call it, to be more precise, is electric vehicle service equipment. Or sometimes we also call it the charging point. So there's two different kinds of chargers, AC and DC. So this diagram Ali has explained just now. So an AC charger basically takes an AC supply and charge the car. So this is the vehicle. And the AC charger that we talk about, that we buy, is actually this device. It's actually an intermediate device between the grid and the EV. So what is very important here is the charging power electronics or the power converters that converts from the AC of the grid, alternating current of the grid, into the high voltage DC. Okay, this one is maybe we just consider as DC, okay, DC voltage. The conversion actually happens on a piece of device within the car itself that is known as onboard charger, OBC, onboard charger. So you can see the AC charger is more of an intermediate device. It doesn't include any power electronics that converts the AC to DC. Whereas for DC charger, a DC charger actually takes out the conversion from the vehicle. So the EV is here. So what happens is that a DC charger will take the AC grid, it will convert the AC grid directly into DC grid, DC voltage. So this voltage usually is around 400 to 800 volt, depending on what kind of charger we're talking about and what kind of EV we're talking about. And it goes straight into the battery. It goes straight into the high voltage battery in the EV. So this is a DC charger. So a DC charger is also known as an off-board charger because it's not in the EV, but it's outside the EV. And the DC charger or DC fast charger contains all the power electronic converters required to do the conversion from AC to DC and control the voltage required to do the charging of the battery without damaging it. So now we know that an AC charger is actually an interface between the grid and the onboard charger. So what is actually inside this interface? So if we look into an AC charger, we can see that there is going to be inputs for the AC power supply to come in. It will go through a protection circuit. So this protection circuit basically is to protect against overcurrent, and is protect against leakage. Because EV charger is something that is involving human touch. So you'll be holding the handle, you'll be charging the car. So it's very important to make sure that there is this residue current device to protect against leakage. So then there's a contactor, which usually is normally open. So the power is not supplied directly to the EV. Instead, there is a controller that controls the charging. When you plug in the cable between the EV and the charger, so the EV onboard charger will talk with the controller in the AC charger. So this controller will decide whether or not the EV is ready to receive power. So once the EV confirms that it's ready to receive power, a signal will be sent to a contactor that basically energizes the contactor here and supplies the three-phase power to the EV. And now the power will be ready to EV so that the EV onboard charger can start to charge the battery. So of course you can see here, this is quite a simple circuit. So the communication here mainly involves a communication between the controller, the charger controller, and the onboard charger. So this is what we usually know as a dumb charger. So Ali and I usually will call this kind of charger as a dumb charger, because this charger basically what it does is you plug it in and it starts to charge when it's ready. It stops charging when it's done. Okay, so we have another kind of chargers that is called a smart charger. So now we have smart grid, everything smart, so we have smart charger. So a smart charger essentially has the same fundamental components as a dumb charger, but it has additional communication that allows exchange of information with the cloud, internet. So basically, apart from having the in-situ kind of communication between the car and the charger, this information of charging, as well as the control of the charging, can be done through the internet. So this provides a certain IoT feature. We can say that this is a kind of IoT feature that allows the charger to be smart. So there's a lot more features that can be employed onto this. So as a matter of fact, one very famous association is Open Charge Alliance. So they have introduced a communication protocol called the OCPP. So this is now the most widely adopted charging protocol for EV chargers. So basically what happens is that you might have a charger, or we call it the EVSE, electric vehicle supply equipment. You can have EVSE of different brands. Like now in Malaysia, the very common one, you can have Eiger, you can have a BMW charger, you can have ABB charger. So all these chargers will have a different way of communicating with the car. But it's very important for you to be able to talk to all the chargers using the same protocol. So by using a common protocol called the OCPP, then you are able to actually control the charger through the EV user, through your apps, and you can actually communicate with your charger by starting and stopping the charging, or whenever there's any charging that occurs, the information of the charging in terms of the time, in terms of the power consumption, in terms of status of the car, can be sent through the cloud and back to the EV user. And if you are, for instance, maybe you are a developer, you are trying to install a lot of chargers at different developing, you have maybe commercial area, residential area. So you need to actually check the charging status, summary of the charging status. So you need to talk to your chargers. So smart chargers with onboard communication device will allow us to achieve this. So that's why we consider it a smart charger. So regardless whether it's dumb or smart charger, so AC charger have the similar control approach. So currently, the most common control approach is based on the SAEJ 1772 standard. So of course, this standard is also being described in IEC 61851-1. So if you look at the charger, we have different connectors. Just now, some of the audience were asking about, is there any standardized connectors? So far, as you can see, the connectors development evolved around different economic zones. So we have a zone that is represented by Japan and US. We have a zone that is dominated by Europe, particularly Germany. And we have a zone that is dominated by Italy and France. Of course, China, with the Guobiao GB standard, is also a rising competitor in terms of standards. So, of course, I believe that in order to allow the trade and equipment to cross boundary, it's good to have a unified connector like USB. But currently, it's money issue. It's a market share problem, so it's a bit challenging. But nevertheless, even though the shape of the connector is different, as you can see here, the AC chargers that we can find in the market now, they have a similar communication protocol that allow the charger to communicate with the onboard charger in the car and do the charging. So you can see here, of course, we must have 3 connectors in at least for the AC grid. Okay, for the Type 2 charger connector, we can have for 3-phase, we'll have 4, line 1, line 2, line 3, and neutral, plus 1 ground. Okay. Then the key to the communication is actually the proximity pilot and control pilot, which is known as the PP and CP pin. So these 2 pins are the pin that actually talks between the charger and the EV. So if we look into the circuit, so what is actually inside this PP and CP? So I'm going to give some brief description on how this thing works. And maybe by the end of the course, you might want to fabricate your own charger so you can save some money. You can build your own charger. So on the charger side, we have actually a EVSE controller. And we have a connector. On the EV side, we have a connector, the vehicle inlet. And we have the vehicle controller, which is actually in the onboard charger. Okay, the circuit here looks quite complicated, but I have simplified a bit. Okay, so what we need to know is that for PP, so PP itself is not mainly for control. The proximity pilot, or in some document, they call it the proximity detect. So this is actually a pin that do 2 functions. One is to let the charger knows that the EV has plugged in. So once you plug in the EV, the cable into the charger, so the charger will know that the EV has plugged in. So this is the first function. The second function is to know the cable current capacity. Okay. So just now we have talked about the AC charger has different power rating. If you look at the market, the power rating of the AC charger usually is in discrete value. It's a 3.7 kilowatt, 7.4 kilowatt, 11 kilowatt, and 22 kilowatt. So what actually these numbers means? So this represents the 230 volt at different current level. So if we have a single phase 230 volt at 16 amp, so you are going to get 3.7 kilowatt. So you have 32 amps. So single phase 16 amp, you get 3.7 kilowatt. 32 amps, single phase, you get 7.4 kilowatt. So if you go 16 amps at 3 phase, you get 11 kilowatt. If you go 32 amps at 3 phase, you get 22 kilowatt. So you can see that most of the chargers are oriented in this way because of the voltage rating and standard current rating that's available in most of the electric equipments. Cable, circuit breakers, all they're using 16 amp, 32 amps as a cutoff point. So that's why the power rating is designed that way. Okay. So the cable also has a current carrying capacity. So if you buy electric cable, you're going to find that the electric cable is quite expensive. So that cable itself is usually made from copper, good quality copper, to make sure that there's no chance of burning. And it has a certain current rating. So this current rating is actually marked by having a resistor between the PP, the proximity pilot, and the protective ground of the cable. So if you buy a cable, you can use a multimeter and check between these 2 points, and you're going to see the values of the resistance. And this resistance will represent the current carrying capacity of the cable. So if, for example, if your charger is designed, if you have installed a charger, 3.7 kilowatt, 16 amp, so if you are using a cable that is going to draw 32 amps, so there's going to be an error. So there must be a matching between the maximum capability of your charger and the maximum capability of your cable. So the proximity pilot provides that protection as well to identify the cable current carrying capacity. Okay. The most important part that starts and stops a charging is actually the control pilot or the CP pin that we said before. So based on the SAE J1772, there is actually 5 states: state A, state B, state C, state D, and state E. So state A is not connected, state B is EV connected, ready but not yet charged. State C is EV is charging. State D is EV is charging, but it requires ventilation. And state E is error. So you can see here, the voltage here is plus minus 12 volt. So when you move from one state to the other state, the voltage on the positive part will drop. So this is 0. The voltage on the positive part will drop to 9 volt, to 6 volt, and to 3 volt. Whereas the negative here will maintain at minus 12. So how this is done? So I have drawn a simplified circuit of the CP. So this represents the AC charger part. This represents the EV part. So basically, what they have in the AC charger is a power generator and the power supply and some relays. So when the cable is not connected, by default, the relay is connected to 12 volt. So if you measure the point here, you measure the voltage here, you're going to see that it's 12 volt. So this means that no cable has been connected. So once the cable is connected, so when the cable is connected, initially the switch will be in this position. So 12 volt, when you put a resistor of 1 kilo ohm together with 2,740 kilo ohm, you're going to see that the voltage here is going to drop from 12 into 9 volt. So a drop from 12 to 9 will indicate that the connection has been made between the charger and the EV. Once it's ready, the EV charger is going to switch S1 into the position that is connected to the power generator, and a PWM, a pulse width modulated signal, is going to be generated and can be measured by the EV charger as well as by the EV onboard charger. So the AC charger will measure here, the EV can measure here. So they're going to see essentially the same thing. Of course, the diode will change the priority, but they are going to see the same magnitude on the positive side. Okay, so once the state B has commenced, that means that EV is charging. So then the charger, the onboard charger, can get ready to charge. So you can see, because the AC charger doesn't contain any power converters, the charging has to be started by the EV. So how the EV can start the charging is by controlling switch 2. So if the switch 2 is turned on, means that the onboard charger has decided to start charging. The voltage will drop down to 6 volt now. The voltage will drop down to 6 volt now. So this will tell the charger that, okay, the onboard charger is now charging. So the charger can send a signal back. So if you're using a smart charger, the charger will send back to the cloud saying that charging has started. Okay, so the charging will commence at this point until, if nothing happens, then it will remain in this state until the charging is full. But because for battery charging, the temperature of the battery has a very profound impact. For some of you guys would already own the EV, so you realize that on hot days, your charging usually has a lot of start-stop session. So what happens is that you will see that charging will start, then after that charging will pause, and the car will go into ventilation mode, where you can hear the sound of the fan. Then the fan will stop, then you go back to charging. So this kind of mode is common. So in order to have that mode, so you need to have another resistor that is in parallel that has to be connected. So this will bring the voltage down to 3 volt. So not all the chargers will go into the state D. So this is an optional state. So because state E, by grounding the pin to 0, that indicates that the charger is having a problem. So you can see by playing around with the switches on the onboard charger side as well as AC charger side, communication between the charger and the EV can be established. Okay. So at the same time, the EV charger is actually communicating to the charger in terms of what is the current that is being drawn. So how the current is being drawn? Because we are using a pulse width modulation, one more degree of freedom that we can play around is actually the on time, the duty of the switching. So the switching pulses here is 1 kilohertz. So we're talking about 1000 hertz. So it means that it's 1 millisecond. From one cycle is 1 millisecond. So it depends on the on time. So the on time over the total period is the duty cycle. So when I vary duty from 0 all the way to 100, then that indicates the current level from 0 all the way to 90 amps. So these are 90 amps. So you can see there's actually a point here. So at about 51 amps, there's these two different curves. So anything below 51 amps is going to have a linear relation, which is 1% is equals to 0.6 amps. So above here, if the charger requires a much higher current, then the SAE J1772 allows that for very high duty cycle. But at this point, the resolution is 2.5 amp per duty cycle, per percent of duty cycle. So, but usually we operate less than 32 amps. So we would not have this, we usually don't operate beyond this 85 and 90% of the duty cycle. Okay, so until this point, we can see that an AC charger basically is a protection, and in some cases, communication for onboard charger to do its job. Oh, sorry, so the communication, it must always be there. So the communication is done through CP and PP. So protection is through the circuit breaker and also the residual current device. So AC charger can be either dumb charger or smart charger. So that's why you can find actually some chargers, they are really, really cheap. So as a matter of fact, if you look online, you can see there are some projects that they actually build a charger by just implementing a circuit like this. So you can build an Arduino, you can put some circuit, some relays, some resistor. You can actually make the charging occur. But of course, the safety and the quality of the component is a different issue. So the good charger usually should be equipped with the smart feature, smart communication feature, means that it should have some sort of IoT that allow us to do a remote control and remote monitoring of the charger. So we believe that the smart charger is going to be the future. Of course, a dumb charger is fine if you are just using it at home. So you just want a charger that works. So as long as the charger fulfills the IEEE standard and the CRIM standard in terms of all the components, then it should be fine. But if you are talking about public chargers that you need to have users of different origin to use it, then you might use a smart charger to have more control over the charger. Okay, so limitation of AC charger. So AC charger is very simple. So there's not much issue. So what's actually the limitation of AC charger? Why people want to spend tens of thousands of ringgit or hundreds of thousands of ringgit to install DC charger? So of course we know, based on what RLE has presented, the speed is a problem. But why is AC chargers not able to deliver the speed? So the key here is because the AC charger is not really a charger. The AC charger is just an interface. So the charger is actually in the car, the onboard charger. So if we talk about the car electric vehicle, so the most important part of electric vehicle, of course, is the battery, the inverter, and the motor. So these are the three things that actually drive your car. Without these three elements, so the electric vehicle will not be a vehicle. It cannot move. Okay, onboard charger is important for us to do the charging, but it's not the core element of an EV. So in most design, we want to actually reduce the size of onboard charger to a point that is just enough to do the charging. Because during operation, when you're driving the onboard when you're driving an EV, the onboard charger is practically dead weight. It's not being used. So this dead weight is going to occupy space and you're going to reduce efficiency. So if you can see here, like we have, this is a first generation onboard charger for Nissan Leaf by Dichicon. So they were the company that actually do the onboard charger for iMIF as well. So this is quite bulky. So this is actually a Tesla onboard charger. It's also quite big in size. So there are many components that you can identify here. The capacitor, the inductor is usually the big thing here. So inductor is a big coil that is required in order to smooth out the current. So just now, one of the participants asked about the power quality issue. So if you look at the construction of an AC charger, you can see that AC charger doesn't have a lot of power electronics inside. So the main thing that is going to affect the power quality of an AC charger is actually the onboard power supply. So you need to have an onboard power supply to actually supply the controller. So it's just something similar to a power supply of a laptop. You need to run it to have the microprocessor to do the decision. So that power supply is usually very small. So the rest of it, the circuit breakers, the contactors, it doesn't pose a lot of significant power quality issue. So AC charger by itself, it doesn't create a significant power quality issue. But once we are doing the charging through an AC charger, the main component that actually poses power quality issue is the onboard charger. So it means that for the same AC charger, if I charge a Nissan Leaf, if I charge a Tesla, if I charge a Mitsubishi iMIF, the power quality that I can measure is going to be very different because the onboard charger that is used in the Nissan Leaf, in iMIF, in Tesla are using different topology and they're using different control algorithm. So it's not very fair to say that, oh, if I measure the charging of this charger, okay, this charger is not good. Maybe it's not because the charger is not good. It's because the car onboard charger is not good. It's not the AC charger. The AC charger is just an interface. So for those of you guys who own the EV Renault Zoe, you know that Renault Zoe is one of the most fussy car, EV. So you'll find that in some occasion, you go to a certain charger, the Renault Zoe doesn't want to charge. So this is also because of the onboard charger. So later, I'm going to describe a bit about Renault Zoe. So they have a different topology for their onboard charger that make them a bit more fussy. So a French car, so they are a little bit different. So the design is slightly different. But it's very interesting. It's a very beautiful piece of technology, but it has a certain limitation because of the advantage that it provides. Okay, so we look at this. So the onboard charger becomes the limitation in terms of the charging power because we want to reduce the size to just nice. So let's look at this. This is, I think it's from Tesla. So this is from Tesla website. So Tesla is one of the most powerful EV available in the market at the moment. So, but the charger option that comes with a Tesla car is 11.5 kilowatt and 17.3 kilowatt. Okay, so this is so just now remember we talked about 11 kilowatt charger. So this one is something in between because it's using 72 amps, 48 amps. Okay. But what is interesting is why am I talking about the charger here? The charger here is not more than 20 kilowatt, but the power capability of the Tesla is more than 300 kilowatt. So it means that onboard charger is only supplying a fraction of the capability of the traction. So this is because the requirement to reduce the size of the onboard charger. Okay. So we are talking about traction. So just now we say that the most important part for EV is the battery, the inverter, which converts from DC of the battery into AC for the motor. Okay, so these three components are the core component for an EV. So when the power flow from battery to the motor, this is the traction power. So this is the power that we use to drive the car. So when the motor is brake, so when you press the brake pedal, unlike ICE car, if you press the brake pedal for internal combustion engine vehicle, the energy from the car is going to be dissipated as a form of heat through the brake pad. But if you use an EV, when you press the brake, so what happens is that the motor will become a generator. It become a generator, and then the power will flow back to the battery and charges the battery. So when you become a generator, the motor has a braking power. So you slow down the car. So in this way, that's why EV is considered more efficient than the ICE car because of this ability to have a bi-directional power flow. For petrol car, when you press the brake, we cannot generate back the energy back into petrol. So there's no way to do it. So onboard charger works this way. So onboard charger basically is an additional device, usually contains two main parts. One is a power factor corrector. So one is a DC-DC converter. So the power factor corrector is exactly as what your friend has asked just now. This is for the power quality. Because all these are power electronics. So there's a lot of high frequency switching that occurs within the power electronics. So you need to have usually some sort of LC filter, an inductor and capacitor filter with some switching device in order to correct the power factor, the power factor, to make sure that we don't have a significant impact to the grid when we connect the EV for charging. There's quite a lot of documents on different topologies. As a matter of fact, every day you will see 5 new topologies being introduced, some small modification. But in terms of industry-wise, a very common one is these few topologies. So on the power factor correction part, the common one is to have a diode rectifier. So if we have a single phase AC coming in, you go through a diode rectifier, and you have essentially a boost converter. So this converter is going to chop it. By controlling this switch, we can have a certain degree of control over the quality of the the current that drawn in. So if we only have a diode rectifier without this chopping state, so the diode rectifier is known to have a very significant harmonics issue. So of course we can improve it. So if we, instead of having just one chopper, we can have 2 choppers. So basically you can have L1, D1, and switch 1 as one chopper, and you have another one in parallel, L2, D2, and switch 2 in parallel with the first set. So in this case, we can have what we call as an interleaving. So I'm not going to go detail about this one, but it improves the current ripple quality. So if this current ripple is going to be like this current ripple is going to be smaller. The ripple can be half. So it improves the power quality of the circuit. So essentially what occurs in this stage is it converts from AC into DC while maintaining to a certain degree a good power quality. So the diode rectifier itself can convert from AC to DC. But by adding the chopping state, we can improve the power quality. So we have some DC voltage here. But this DC voltage cannot be controlled to a good degree. So in order to make sure that we have a good control of the power, the power that flows to the battery, to charge the battery, we need to have another stage, which is a DC-DC converter. So this DC converter will switch the DC into another matching DC that is required by the battery at that particular charging state. So usually the onboard charger requires some sort of isolation. So an isolated transformer is used here. But for those that have been working with transformer, you know that transformer is one of the most bulky equipment in power system. So to reduce the size of the transformer to a size that can fit into a car, we are using a DC chopper method here. So what happens is that this circuit is going to generate an AC signal that is having very high frequency. We are not running at 50 kilo. We are not running at 50 hertz. We are running at a few thousand or few tens of thousand kilohertz to generate the frequency, high frequency. They allow us to use a smaller transformer. So this transformer can be reduced. And again, we go through another stage of diode rectifier to get the desired voltage that can charge the battery. So these two parts, a power factor corrector and a DC-DC converter, are the 2 core components of any onboard charger. Okay, back to just now. So we are talking about the power rating. So these are a few common onboard chargers available in the market. So like this one by Delta, that is used in Chevy Volt, GM Chevy Volt. So it's 3.6 kilowatt. The Nichicon is Nissan Leaf is using 6.6 kilowatt. Tesla 11 to 17 kilowatt. Okay, compare with the drive power. So the battery itself is 16.5 kilowatt hour. This is 20. So now the new generation Nissan Leaf is 40 kilowatt hour. So Tesla is 100 kilowatt hour. So you can see the power here is only a fraction of the capability of the battery. So that's why AC charging is usually considered slow. The limitation of AC charger, why is it slow? Is because the power is restricted by the onboard charger. The battery and the drive can take high power, but just that onboard charger is not able to provide that power. So that becomes the limit. So if you want to increase the onboard charger, we have to increase the size, and we're going to increase the dead weight on the EV, which is not a good idea for EV design because it will drag down the efficiency of the whole car. So that's why they introduced off-board charger, which is a DC fast charger. So what happened is that for DC fast charger, the power electronics that converts the AC grid power to the required DC power is shifted outside the car. So in this case, it can be as big as possible. So that's why in the first picture that we show, a DC charger usually has a very big cabinet. So you can contain the power electronics, the inductor and capacitor, which is much higher, 10 times, 20 times higher than what usually an onboard charger can offer. So instead of connecting through any power electronics, it goes straight to the battery, because the battery itself is able to take that high power. As a matter of fact, the battery itself is always giving high power to the motor. The power is not the problem for the battery. The power is the problem for the onboard charger, which is now no longer needed. So similar to the onboard charger, the off-board charger also contains two main parts: power factor corrector and a DC-DC converter. So this topology is the most common topology. So this provides certain side of isolation, protection. This provides some sort of power quality control. So of course, because the size is no longer a constraint, so the DC charger has a bigger power, and usually it runs on two phase. There's no point for you to run on single phase for DC charger. So like one of the charger that we have installed in Malaysia is the ABB, the Terra HP 175. So there are different forms of chargers, DC fast chargers that is being offered. So they have different variants in the way they construct. So for ABB case, for instance, they have split the chargers into two parts. So you have a very bulky power cabinet, and you have a very sleek, nice looking charger post. So the power cabinet is usually hidden behind the scene, it's away from the EV. So this handles the bulk conversion of AC to DC. So the AC input power, the power will come from the AC cable. You convert into DC. And this DC power is being sent through underground cable into the charge post. So the charge post will have the DC power ready to charge the EV. It doesn't need to have the AC to DC conversion here. So the DC conversion is all done in the big and bulky cabinet. And you can have a very nice, sleek-looking charger post near to the EV user. Of course, they usually give a single-phase utility power, or sometimes three-phase, in this case, three-phase utility power, to power up some of the auxiliary equipment inside the charging post. Okay, if we look at here, the trend is that more and more cars, especially new cars, they are all equipped with a certain degree of DC charging. Because AC charging is good. If you want to deploy EV, you want to encourage people to use EV. The first thing is you must provide capability to charge at home or at work using AC charger. So this is the basic requirement. So if you can provide that, people will be willing to buy EV because they know that, okay, there's some place for me to charge. If there's no place for me to charge, I worry that if I buy an EV, so where can I charge my car? So AC charging is a basic requirement. So, but AC charging has a limitation because of the onboard charger. So nowadays, the new cars are all equipped with a DC charging option. In most cases, the DC charging is a preset. So you can charge with AC as well as DC. So the AC should always be there. The DC sometimes is optional. So in this case, DC usually is preset. So they have always a DC charging capability. So the DC charging will allow now, I think the fastest one so far is Porsche Taycan. So they allows up to 350 kilowatt charging. But that one requires a higher battery, higher voltage battery. So for most of the EV batteries, the battery usually is 300 to 400 plus volt. So it doesn't go higher than that. So Taycan, because of the very high charging requirement, is using 800 volt. Okay, this one is a repeat of what I earlier has mentioned. So similar to AC charging, the DC charger also have different standard. We have the CHAdeMO standard and the CCS combo standard. So these two are the most common one. Of course, the Guobiao, the China standard is also up and rising. So what is the main difference between these two charging standards? Okay. One, of course, it's a communication protocol. So for CHAdeMO and GB, they are using CAN. They are using CAN for communication. So they need to have a designated pin for CAN communication. For CCS combo, they're using power line communication. Means that the communication is using the power line itself. So they do not require additional pin for communication. So if you look at this, the top here is for AC charging. So it has the same 5 pins or 3 pins for single phase or 3 phase, and also the PP and CP. It's the same thing, PP and CP. So the DC one is using the just positive and negative. Whereas for the Chademo, you have the DC, you do not have an AC. This is called combo because you have an AC plus a DC. So within one socket, you can do an AC and DC. For Chademo, there's no AC, there's only DC. So that's why just now in the slide presented by IEEE, for Nissan Leaf, for example, so they need to have 2 different sockets. So they need to have a socket for AC, they need to have a socket for Chademo DC. So Gobia also the same, so they need to have separate, and they have additional pins for the communication, for the CAN communication. Okay, so DC fast charging. So fast charging is actually good because it allows us to have very fast replenish of the range within a short period of time. We're talking about minutes. Okay, but fast charging is known to be very damaging for the car. As a matter of fact, when we talked to Nissan, they were saying that it's not advised to have too frequent fast charging. So fast charging is only for purpose like when you want to go outstation. So you need that juice within a short period of time. So you do it once a day, so not multiple times a day. So we actually did some search on the patents by Tesla. So this is by Tesla. So it's mentioned that the fast charging actually reduced the life. So what Tesla has found, he has found a few patents. For those who are interested, you can go to Google Scholar and search the patents under Tesla. So they were actually coming up with different charging methods that allow the fast charging to be done without damaging the battery so much. So this is one of the methods they were proposing. It's a multi-stage. So a common way of charging a battery, whether it's our handphone battery, whether it's our lithium battery, or even fast charging, is we have 2 states. One is common current, one is common voltage. A common current means that we fix the current to a maximum that is allowed, and we charge it up, and the voltage will increase as the battery gets charged up. So when the voltage hit a maximum voltage, we will fix the voltage without letting the voltage increase or even damage. So you look at here, at constant current charging, the current will first go up until it hit a maximum limit defined as, in this case, Tesla defined 4.05 volt as a limit. So he will keep the voltage at 4.05. So until a certain time, until certain SOC, then they will again allow the constant current to charge up to the next voltage limit, which they define as 4.2. So this multi-stage charging, according to Tesla, allows the battery to charge at 2C without damaging the battery. So this is a more recent research work. So it was proposing actually to have a rest time between the constant current charging and constant voltage charging, so that you can have a longer lifetime. So in this case, they suggest to charge at 2C until 60% of SOC. Then you rest for 5 minutes, followed by a 0.5C until you go into the constant voltage. So this is 0.5C and this is 2C. So this part of different charging algorithm is actively being researched, and it depends very much on the construction of the battery, how the battery is designed. So this, I'm not really expert, so I do not want to say so much. So this is quite an interesting site by ChargePoint, one of the biggest charging facility provider. So here again, it shows that how the charging curve depends on the car. So just now we mentioned that for AC charger, the charger is only an interface. So the onboard charger is the one that do the charging, they decide the charging and affect the power quality. Okay, how about for DC charger? Okay, for DC charger, the power quality is undoubtedly depends on the DC charger itself, because the power factor correctors, the DC-DC converters are all within the DC fast charger. Okay, but the charging shape, so how the power is being delivered, depends on the car. So this is actually from the same charging DC fast charger. These 3 waveform come from the same DC fast charger. I think it's able to produce around 60 kilowatt. So depends on the car, the charging waveform is different because the car is communicating with the DC fast charger to provide a different charging current that is suited for the battery on the car, and also depends on algorithm of the car manufacturer. So for example, the Chevrolet, you can see that the power goes very fast up to about 30 plus, they slowly go up all the way to 75, about 50 kilowatt, 48 kilowatt, then it goes down, taper down before it goes down. Whereas for Jaguar I-Pace, it go all the way up to maximum, 60 kilowatt, stay there until a certain point, it start to go down. So actually, this way of charging, Tesla also have a pattern here. They call it a negative slope charging. So it means that once you have reached a certain SOC, it will provide a current, a power that goes down by a negative slope. So this is also, Tesla has patterned something similar. There's a certain advantage to this. I do not know the detail of this because I'm not a battery expert. So maybe some of you guys can comment on this. So for i3, you can see similar, how it rises up very fast to as high as possible. After that, it slowly goes up before very fast going down. So this is different charging curve for the same charger but different EV. Okay, so just now I mentioned about Renault Zoe. So for those who own a Renault Zoe, they know that Renault Zoe is a very special, very special car. Okay, first is by looking at the Renault Zoe. It's quite a small car. It's a compact sedan. It's about the size of a Myvi, so not very big. So you compare with other cars like Tesla or Leaf, this is considered smaller. Okay, but what is quite interesting is that, remember that Nissan Leaf has a 6.6 kilowatt onboard charger, and Tesla have 11 to 17 kilowatt charger. So these are the leaders of EV. But for Renault Zoe, it has a charger that can go up to 43 kilowatt. This is they call it the Q90 variant. So the normal one, it can go 22 kilowatt. So even the normal one is higher than Tesla. So for a car size of a Myvi, it's having an onboard charger capability higher than Tesla. So that's quite puzzling. At first, when we see this, we are quite puzzling that how we actually allow this. So when we look into the Renault Zoe, it says that they have this, they call it a chameleon charger. So this charger allows the capability of a DC fast charger. So this is way back when Renault Zoe was introduced, DC fast charger was providing about 20 kilowatt. So now 50 and 60 kilowatt is the norm. They say that they can provide higher than the fast charger at the time by giving 43 kilowatt at a fraction of the size of a fast charger. So that's very particular because we know that the problem with an onboard charger is the size. So if we want to increase the power, we need to increase the size. So there's no other way around it. So Nissan and Tesla has followed the common way of doing it, and they ended up with a small charger. For Renault Zoe, they have actually used a concept called an integrated charger. Okay, remember just now we mentioned that the key element for EV is a battery, DC-AC converter or inverter, and the motor. So these three must be in the EV. An onboard charger is actually optional. Okay, but we need onboard charger to provide the AC to DC conversion. Okay. What if we can use the AC to DC converter and motor as a charger? Can we use this power electronics and the motor as a charger? So if we can do that, we know that the capability of this power electronics and the motor is very high. So they can handle hundreds of kilowatt. So it's not a problem to supply high power. So this is exactly what Renault has proposed. So Renault has a patent 2012. So in the patent, he actually proposed the concept of an integrated charger. So what happened is that they have a chameleon charger, which essentially is the power factor corrector state without inductor. So in DC-DC converters, for those who has done power electronics or those actively involved in power system, you know that inductor usually is very bulky. So capacitor can still be quite small, but inductor usually is very bulky and very heavy. So this is the key problem. But at the same time, a motor, when it's not rotating, is also an inductor. So what Renault Zoe was proposing was, can we use the inductance in the motor as an inductor, and we just add some power electronics and a filter capacitor at the front, so that we can take the AC power and convert it into DC power that goes straight into the battery using the high power inverter. So in this case, the inverter is going to operate in the regenerative mode to flow the power backwards. We know that the inverter itself is always capable of running regenerative mode. So this is not the key feature of EV. So this is not a problem. So the key thing is that how do we play around with the configuration here? They allow us to convert from AC to DC. At the same time, the motor cannot move. I must make sure that motor doesn't rotate when we do the charging. So this is done by using the zero sequence current. So for those that do power system and electrical engineering, you know that zero sequence current, it doesn't create any rotation. So zero sequence current is flow through the neutral point of the motor, and it goes equally into the three phases, and the motor doesn't turn. So this allows the charging to occur by having some power electronics here, which the size can be reasonably small, and we rely the bulk power by using the existing power electronics and inductor in the drivetrain. So this is quite a genius solution. But this solution has a setback. The first thing you can see that compared with the onboard DC-DC converter, the onboard charger that we see, onboard charger has a power factor corrector connected by a DC-DC converter. So this DC-DC converter usually provides some sort of isolation. So in electric system, isolation of power electronics is good because it prevents a leakage current to flow from the power system to the load. So in this case, our battery side, when we have a switching, there is a chance that there is a leakage current that can flow within the power electronics and the ground. So this will trip the RCD, residual current device. So this is not good. So as a matter of fact, there's a lot of feedback for people that own Zoe, that Zoe has a lot of problem charging in some charging station. So if the charging station has a grounding issue, the grounding is not good enough, you will see that the Renault Zoe refuses to charge. So why? Is because of the leakage current. So a motor itself, a motor has inductance, that's true. But at the same time, motor is known to have a certain leakage connecting to the body of the motor. So this is a leakage capacitance. So this leakage cannot be controlled or isolated like in a normal inductor. Because if you want to construct the motor, you have to construct in the motor way. So when you do it that way, the capacitor will appear as a parasitic capacitance. It cannot be completely eliminated. So Renault actually they realized this, and they also filed in 2014 another patent of controlling the rectifier here in order to reduce the leakage current across the capacitor. So they realized that the capacitors appear between the motor and the grounding cause a high leakage, and they need to have a special way of controlling the switches in order to minimize this current. So this way of controlling still requires a good grounding. So if your grounding has a very high resistance, then actually the way of controlling is not good. So that's why the Zoe will have problem charging. And you can see that this is common because we do not have any isolation. There's a direct connection between the power supply, the grid, to the battery, through the power electronics. So there's no isolation. So the power quality issue is a bit more severe in here. So this is a Renault Zoe charging curve that we have done with the car that we have. So EVC has a Renault Zoe, but it's not the Q90 version. So we can only charge it a maximum of 22 kilowatt. So you can see here, the charging pattern of Renault Zoe is quite similar to I-PES or like Tesla, whereby it goes all the way up to maximum, about 22 kilowatt. Then after that, it starts to taper down, go down in stages before it goes very slow, very low power charging. So the high power charging is usually occurs only for a short time. This is true for most of the DC fast charger. Because of battery chemistry, you cannot force the power going into the battery for too much. So it's recommended that usually fast charging should only be done up to about 80% SOC. So if you go beyond that, the charging which is going to go down very rapidly. So there's no point for you to charge longer time. So let's say if you are charging and you're paying by the minutes, so you might want to charge the car up to about 80%. That's where you maximize the kilowatt per minute that you're going to get. So after that, your charger automatically you're going to bring down the power. So if you continue to keep your car there charging, you're going to get less kilowatt per minute. At the same time, you're occupying a valuable charging time for other users. So it is always recommended to charge up to about 80%. So is Renault the only one that is doing this integrated charger? Yes and no. So yes, at the moment in the market, Renault Zoe is the one that is a mainstream car that is using this technology. But we also saw that Continental is trying to position itself as an EV solution provider. So in the press release in 2017, they introduced something called all-charge technology. So it's very nice. This is an all-charge charging system. So it turns the electric powertrain into universal charger, catering for all types of cable-based charging station. So it can go all the way up to 800 to 350 kilowatt, all charging, single phase, three-phase, and high-speed DC. So he developed an innovative system, which basically a modified electric drivetrain, where the motor and the inverter, which switches between DC and AC power, have been specially adapted to handle the additional task of charging. So now, if you look at this, you can easily recall that it's the same concept as what we discussed just now with Renault Zoe, integrated charging. So I did some search and I saw that this Continental is actually working with University of Maryland. So they have filed a patent that is recently granted, February 2020. This patent was given a preliminary patent in 2016. So they already got the patent out 2016. So that's why in 2017, Continental already announced the technology. But I think the patent takes time. So this is officially given a date of 2020. So you can see here. So they're using exactly the same thing, same concept, but not exactly the same thing. Okay, what is the difference? So here again, you can see there's a motor. So they represent the motor with 3 inductors. This is the inverter, similar to what we see just now, the inverter. And then we have the battery. So this is the 3 core element of an EV. So the additional circuit comes in the form of a direct rectifier. So with this direct rectifier, you say that instead of having a thyristor-based current source rectifier, using a normal direct rectifier, it connects to a specific point around the inverter. So he's proposing a different point compared with Renault Zoe. And then with this, he can actually achieve control. But in this pattern, actually, they are quite good in the sense that they cover quite a lot of things. So if you use a direct rectifier, you can see here, the limitation is that you cannot control the voltage from here. The direct rectifier is a passive device. You cannot control the voltage that is generated here. It depends very much on the supply voltage. So they propose a different way of doing it that allows 3-phase charging and also single-phase charging. Single-phase charging can be done by using just 2. If they connect one single phase across 2 links, they can do single-phase charging. If they connect all 3, they can get 3-phase charging. So they have a bidirectional. They have 3 bidirectional switches here. They allow the charger to perform a burst. And using the inductor here, can provide the power flow. The power will flow from the grid, go through the inductor, go back to the battery. So for those that is interested, you can actually have a look at the pattern. It's quite well explained. So of course, on the research front, there are also a lot of interest to go into this integrated onboard charger by playing around with different machine topology. So one of my colleagues in the UK, so what they are doing is that they're actually using machine with more than 3 phase. So in this case, they have used 6-phase and 9-phase machine. So they show that using this machine, you can have even simpler topology. They can achieve the similar performance of integrated power onboard charger, and you provide a more flexibility of control. Okay, I think that's all that I want to share for today. So I appreciate if there's any question, anything related to the presentation or slightly outside is fine. So I will pass back to the host. So there's a question on how fast in terms of the time for DCFC can do. So we are talking about, if I remember correctly, about 5 minutes we can get about 70 kilometers of range. So it depends on the which car you're talking about, what power rating you're talking about, and also it depends on the SOC that you're in. So you can see just now according to the curve. So the charging curve will go down when the car is almost full. So if you charge the car when the SOC is very low, you can get a lot of SOC within a very short time. But let's say if your car is very close to 80% SOC, so just by charging in a while, you already hit the limit, and the charger will move away from fast charging, go down to the slower charging in order to protect the battery. Okay, yeah. So Dr. Mahdi, you are already expert, so you're asking me a question. This is a redundant question. How to make sure the motor doesn't move while taking zero sequence current? So basically, for those who are working in the motor, this is quite a common understanding. I think so. Dr. Mahdi is trying to highlight the case for those who are not really in this area. Okay. So for motor to rotate, basically what we need to do, we need to provide a rotating magnetic field to the motor. So this is a concept of MMF. So in a usually three-phase motor, for instance, you can see in this diagram here, we can consider a three-phase motor. So we have a phase A, phase B, and phase C. So these three phases, when you supply the current into this three-phase winding, these windings are actually located 120 degrees from one another in space. So if you provide a current that is 120 degrees in time, let's say if I have three-phase current, okay. So A, B, and C. If I have a three sine wave provided a phase shift 120 degrees, and I give to a machine with three-phase winding in space. So what happens is, phase A, for example, let's say phase A will give a magnetic field in this direction, this A. Phase B will give a magnetic in this direction, and phase C in this direction. So the magnetic field is going to be maximum when the current is maximum in that phase. So if I have, let's say, in this position, the B is maximum, the C and A is negative. So B being maximum will provide a magnetic field in this direction. A is negative means you provide a field in this direction. C is negative means you provide a field in this direction. So as a result, I'm going to get a resultant magnetic field that is in this direction. So this is the MMF resultant. So when I move with time, the B will go down. Let's say go down to here. The C will go to positive. The A will go to negative, will remain negative. So what happens is that now I have a B which is still positive, but the magnetic is slower. C, before this was negative, now I go to positive. And A is negative, it's here. So the resultant vector will move somewhere here. There's going to be a shift of vector. So if you plot it along the time, as a time move, you can see that you're going to create a rotating magnetic field. So this occurs because of two things. One is that the current is 120 degree phase shift in time. And the second thing is the winding is 120 degree phase shift in space. So both these conditions must be satisfied. Then you create a rotating magnetic field, and this creates the torque to rotate the rotor. Okay. What this integrated charger do is that now instead of providing three sine wave that is different, when I connect it, let's say the Renault Zoe case, okay, when I connect it in this way, you can see that there's only one current that coming in to the neutral. The same current will be divided by 3 and going into all the three phases simultaneously. So if this is I, then all the current is going to be I over 3. So if I have the same current, means there's no phase shift in time, then rotation will not occur. So there's no rotation. So if I do not have a rotation, then I do not create a movement on the rotor, and the rotor will not move. I hope that explains. Any other questions? So anyone has any questions, I think feel free to drop an email or something. So the motor inductor is quite interesting. This is quite interesting. Oh, Prof. Nick. Oh, we have an expert on motor here, Prof. Nick Rumsey from UTM. Hi, Prof. Actually, I'm not too familiar with Tesla supercharger because Malaysia, we don't have the supercharger. In Malaysia, we have, my personal experience is with EVC. So far, we've installed 2 chargers. One is a China brand charger. Another one is ABB charger. So the technology is a bit different. So as far as I know, Tesla charger has a maximum voltage about 400 plus. So it's not suitable for other brand. And the connection is also different. They have a proprietary system. So it's only for Tesla. It's a bit, it's like Apple, you know. You have to use a lightning cable, you cannot use it for Apple. So Tesla is playing that game. So I wish to know more. If there's some information on Tesla supercharger, I wish to comment more. But unfortunately, I do not have first-hand experience on that. It's a business model. As IEEE has shown, Tesla has become so successful. What is interesting is that why China is putting a lot of money on EV is that EV is one of a way of taking a shortcut to win the automotive race. So if you want to compete with cars like BMW, Volkswagen, Hyundai, Toyota, in terms of ICE car, it's going to be quite challenging because the brand is already being fixed. People know, okay, if we talk about Toyota, we know, okay, what is the brand perception? We talk about BMW, we know brand perception. But when it comes to EV, it's almost like a level ground. So Tesla managed to cut queue and actually obtain a dominance in the market by coming into a new market. So China was trying to do something the same as well. So by going into EV, they actually managed to push companies like BYD and BAIC. So they become the leaders in EV, beating companies like Nissan and BMW. All these, they are only coming. So this is actually quite interesting. Tesla has proven they're quite successful. We don't know how it goes, but being stingy as they are quite successful in building the brand. Well, thank you very much, Prof. So, so maybe I will pass back to the host. Dr. Harun, is there any more questions from the YouTube side? We can only see the presentation. I can only see the comments in the WebEx. All the pictures there have been properly referenced. Can. Okay, so no problem. I can share the slide. I will send the slide to Dr. Harun, I think, for the presentation. Except Zoe, he said universal charger.
I think that's all, Dr. Aaron.
I think there's one question here. Except Zoe, is it possible to have a universal charger, maybe CAN bus emulator? Actually, Zoe is not really using CAN bus per se. Currently, Zoe is using just a normal AC charger. I don't know. Yeah, so the CAN bus emulator, if for those who are actually trying to study the charger for using Chademo, for example, then they need to have a CAN bus emulator to actually do the communication. Yeah, for those who want to ask some other questions related or not related, feel free to drop me an email. So my email is hsche@um.edu.my. It's on the first page. So after that, you can find that I will send the slides to be distributed to everybody through, of course, IEEE PES. Feel free to drop me an email.